Now that we've gotten some of the math out of the way, we're going to start talking about this course in general. More specifically, what we're going to start talking about is motion. And the general idea behind studying motion is that motion basically controls all physical phenomenon, or at least that's the assumption. It doesn't really matter if we're talking about moving a ball around or dealing with chemical and biological processes. Things, largely speaking, have their behaviors determined by their structure or where things are. So that's what we're going to start looking at. You can even see this in the biological sphere very, very easily. If you take a look on the screen there, you'll see what looks like a complicated bunch of spaghetti inside some fibers. What that actually is it's a computer model of a rhodopsin protein embedded in a cellular bilayer. The rhodopsin protein are like the yellowish large spirals, and the membrane is all the other stuff. The light blue in the middle is basically the phospholipid tails, and the reddish stuff near the end is the phospholipid heads. And I believe the blue little dots, like the dark blue ones, are actually water. And the idea behind this is you can figure out how something like a rhodopsin molecule works by studying how it is constructed. In other words, you can study where everything in it is and how they move. And if you understand that, you can basically predict all of its subsequent behaviors. And that's just one example of how knowing where things are can be rather important. A second example that you will see on the screen here is actually an ultrasound image of a renal cyst. The cyst is the dark circular spot, roughly speaking, in, I don't know, the center of the ultrasound plot. Now, the idea behind this is, again, if you're concerning yourself with health issues, if you want to go in and cut out the cyst, it's kind of helpful to know where it is. So again, one thing that you want to be able to do is quantify the positions of where things are. And one final example of this might be if you're looking at how biological processes take place. What you'll see on the screen in this last example is a comparison of two pore-forming antimicrobial models. In other words, these long grayish cylinders here, I'll just point towards them, are actually antimicrobial, similar to what you might find in Neosporin. And the idea is, depending on how close they are together, different types of pore can form. The one on the left is the barrel stave type pore, in which there is a continuous bilayer all the way through. The other one is a toroidal pore, in which the bilayer actually bends around. And the idea is whether you get model A or model B solely depends on how far things are apart. So not only is it important to know how far things are apart, it's also important to be able to quantify them, as well as quantify them as they move. Now, what we're going to do here is we're going to talk about different ways in which you can observe motion. The first way that you can observe motion is through a quantity known as displacement. Now, displacement is rather simple, so what I'm going to do here is I'm going to draw a black box here on the screen, and what I'd like you to do is I'd like you to tell me if this black box has moved. Now, if you take a look at this and my recording is working correctly, what you should see is you should have seen the box move from one location to another. This here is the simplest way in which you can tell that motion has taken place. The box or the object that you're looking at is no longer where it was before. You have no idea how quickly it was moving. All you know is it's no longer at the same position it was before. Now, if we were to compare these two, we can take a look at the initial position and the final position. I'm just roughly estimating here. Sorry, ignore that. What we can basically say is initially, based on our point of view, there was some initial position. And at the end of the day, there was some final position. This is basically where we see each of these. And because our point of view can change, right, if you stand up and walk 3 spaces to the left, you'll see these be at slightly different positions relative to where you are standing. We can identify them with vectors. Now, displacement is relatively straightforward. If we went from initial position to a final position, there is a vector, which is straight from where we started to where we ended up, which describes the displacement. Mathematically speaking, this displacement is actually the difference between the final and initial positions. And for displacement, that's all there is. We have no idea how quickly this is going over. We don't really know much about it except for it has changed where it is. If something's no longer where you left it, right? You put your keys in the bin, you come back and they're no longer there. It's undergone a displacement. So motion has happened. And this is the simplest way in which you can describe it. Keep in mind, this displacement has to be a vector. The reason it has to be a vector is we need to be able to distinguish one displacement from another displacement. Right? So we need to know both how far we're going and in which direction we're going in.